Well, we've covered a decent amount of waterfront so far, I would say. We've really been talking about the flow of multiple fluids, typically two phases, but it could be more. It could be air, water, and a solvent. We started off, thank you, with the idea that by using our understanding of interfacial processes, the interaction of fluids with surfaces with other fluids present, that we could kind of understand how they get held, retained in certain locations. We defined kind of capillary models for them, for capillary tubes and for fractures, shown here on the right-hand side, and used that to say something about the pressure difference between the two fluids. And then we developed our understanding of capillary pressure versus saturation curves, this figure on the top left, to be able to describe exactly, for real geological media, exactly what they would be, and kind of identified some important locations. One is that irreducible saturation of water. You can't get any more water than that out of the system. The irreducible saturation of the non-wetting fluid, so that when you resaturate by imbibing water back into the system, that's the maximum residual saturation you're left with of that. And also the PC0, or the bubbling pressure, which is the pressure differential we have to apply to get a bubble pushed into the system. We then went on to talk about the movement of fluids and defined that in terms of breaking Darcy's law up into two parallel pipes, if you like, and where really the relative transmission of the two phases kind of scales with their saturation proportion. You know, we could draw these X plots which define the relative permeabilities. And we also rationalized that they shouldn't be X plots, they should be truncated X plots, which should go here and here and here, if anything, right? To be able to describe this behavior. And we defined exactly how that would affect the volumetric flow rates of two fluids by knowing what their saturations are, if the saturations aren't changing. We talked about the conservation equations for mass flow if we had two phases, how we needed 4 equations to be able to solve for 2 pressures and 2 saturations. And then last time we talked about kind of practical applications of why exactly these materials in situ have this residual chimney, a puddle which might be buoyed up on the water table for L-naples, and that might be a residual chimney in the vadose zone going all the way through the groundwater zone and being buoyed up on a capillary barrier for D-naples. And so we kind of explained all of that in terms of our understanding, if you like, of these fundamental behaviors. And so what we'll do today, I guess it was preordained, if I look at this, guess I could use this side just to scoot through it to see where we are. This looks like last week's stuff, indeed. So we talked about the architecture of these things and how it makes perfect sense given what we know about the capillary pressure versus saturation diagrams. And so that's where we left that there. And so today we'll spend a time, I guess we'll finish this off, and because next Tuesday, we'll start talking about transport of dissolved components carried within porous media. And so today our last part is to talk about unsaturated zone. We'll talk about the concept of matrix potential. We'll revisit our empirical capillary pressure versus saturation curves and relative permeability curves. We've already talked a little bit about Brooks-Corey relationships for defining saturations and developing in log-log space an equation that links saturation to capillary pressure as a very simple relationship. And perhaps most important, in a practical way, we'll talk about these Van Genuchten relations, which allow us to define empirical relationships for capillary pressure versus saturation and relative permeability curves, which would be useful in your work. Yeah, okay, actually, let's go back. And so perhaps it's worthwhile, yeah, so you've seen these, and actually probably doesn't hurt to redraw these about the water table. Yeah, so I guess what I was just saying was that if we look at these things around the water table, you know that these relationships look like. You've seen these many times. They're the inverse of each other. This is capillary pressure, which is related to elevation. This is saturation of water between 0 and 1. And we explained last time that this represents the air saturation. This represents the water that's left in place. And that corresponds to this behavior here. Again, exactly the same fluids that are present, but of course, above the water table, if we look at these behaviors, just to sketch it. Can't remember what colors we used for which. Maybe it was, no, I think it was red for water. Then the pressure differential with depth looks like this. P, this is elevation. And then the two other components were that above the water table, the pressure change in air would look like this. And below the water table, the pressure change in a DNAPL, I guess, would look like this. So these represent the capillary pressures. And this represents the negative capillary pressure, this difference. So they're positive both above and below the water table. And so this diagram is just flipped, and it defines our behavior. And so I suppose the key point here is that these relations are also useful to us in defining relative permeabilities. Don't want to be too pedantic in this because I know you've seen these many times. These are relative permeabilities between 1 and 0, and they can look any way that we particularly want them to look. It's not a bad diagram, that actually. We're missing this saturation here. But as I said, as we came into here, these relative permeability curves could look like this, or they could look like this, or they could look like they really are, and they would look like this. Where this point here is lower than this, etc. These are the irreducible wetting saturation, irreducible non-wetting saturation, etc. Not very good curves there, but you get the idea. And they have hysteresis. So that's basically the points that we're trying to make. So we framed everything in terms of wetting fluid and a non-wetting fluid. It didn't matter whether that non-wetting fluid was air or the NAPL. The behavior was similar, identical really, right, from these curves. And so we don't have to make any particular distinction. And so when we talk about unsaturated flow, which is really what we're talking about today, the things that were developed for unsaturated flow could equally well apply to movement of NAPLs in the subsurface. And so that's the main point that we'll make. And it's just that these techniques between petroleum, flow in petroleum reservoirs and flow in the shallow soil for agronomy have developed in completely different literatures their common behaviors. And so what we'll talk about today is the fact that in the agronomy literature, things are defined in slightly differently. We've already talked about hydraulic head being a function of a pressure head plus an elevation head plus a velocity squared term, inertial head. We always put this to be zero. We don't care what it is. Velocities are so slow in porous media that inertia is not an important component, and we only worry about these two things together. We talk about them both together because this is the swimming pool effect that we're talking about. If we have a pressure gradient, a vertical pressure gradient in a swimming pool, we know that that's not flowing. It's a static fluid, and therefore to look at that transmission we have to think about that.
Is the arrow pointing to a zero? I can't really...
Is this pointing to a zero?
Yeah.
Yeah, this term is zero for
Okay.
porous media. That's all I mean by that. And so we ignore it. So this term here is referred to as matrix potential. This is defined here. You see it written out here. And it's the fluid pressure of the wetting fluid divided by its unit weight. So this would be the unit weight of water. This is gamma. Gamma is equal to density of water times whatever planet you're on. We're on Earth, so it's gravitational acceleration. And in that literature, there are a couple of significant pieces of work which we'll talk about. One of which we already talked about is Brooks-Corey, certainly before you were born, almost before I was born, but not quite, and Van Genuchten, which would have definitely been before you were born.
Would you want to scroll back?
Go and look at the video.
A little up. Or is that right?
So. And so the first, we've talked a little bit about this, but it probably doesn't hurt us too much to repeat it. And you might remember that we talked about the idea that if we have these capillary pressure versus saturation curves, which we just drew on the previous page, we do two things. Capillary pressure, saturation of water between 0 and 1. We can define it by volumetric moisture content, theta, between 0 and porosity, right? Remember from the definition of volumetric moisture content, it's volume of voids divided by the total volume of the sample. And so that's exactly the same as the definition of porosity, which is volume of voids divided by total volume. Line through it is not velocities. And so when it's 100% full of water, then the saturated volumetric moisture content is equal to the porosity by definition. We define a bubbling pressure, PC0, which we've also called PB. And we could divide this through by the unit weight of water. And the reason that we might want to do that is because we're defining it as a parameter here, matrix potential. And so we can define this bubbling pressure through this. And you remember that we said that we'd do a couple of things. We truncate this distribution so that we ignored this part here, so that our scaling would be between, instead of 0 at this point here, it would be 0 here and porosity here. And that we take the log of this parameter and we take the log of this parameter. And so the idea is that if you plot this data in log-log space and start off with this being 0 to n, you get something at the bottom here, this straight line distribution. And I guess I shouldn't do things so cramped, but since I see some of you writing these things down, so we could plot this as log P capillary pressure divided by unit weight, and log effective saturation. And if I remind myself what it is, yeah, okay, so this is between, so it would go from 0 to saturated, it would be something like this, I think. So this would be PC over gamma, log of it, and this would be at a saturation, effective saturation of, saturation is equal to 1, fully saturated. And so pushing a bubble of air into it, you have to overcome the resistance, you increase the pressure, and you move along this curve. So all it's done is it's taken this curved curve here and made it into a straight line, just empirically. There's no necessary reason why it should be a straight line, but it turns out to be a straight line as you change it. And so as a function of this straight line, it's really just responding to this relationship here. And that's saying that at any value of the moisture content, we can define that moisture content as equal to the irreducible moisture content of water, the saturated moisture content, this would be equal to porosity, and this would again be the irreducible moisture content. And the ratio of the capillary pressure and the bubbling pressure. And so obviously, not obviously, but at this point here, this term would be PB over PB, so it'd be equal to 1. And this term here would be equal to the gradient. And so what we could do is we could take this term here and we could just divide through by either the porosity or the saturated moisture content, whichever one you want to choose. So I guess the saturated moisture content is equal to the porosity, right? All the pore space is filled with water, and since the rate, this term here is the volume of water divided by the volume total, then these are the same. And so I don't know whether you want to do it, it's either with porosity, or porosity, or porosity, or porosity, or the same as it's written here, just divided by the volumetric saturated moisture content because of this relationship here. So this term ends up being 1. These terms all end up being saturations, right? The proportion of moisture in it relative to its saturated proportion is just equal to the saturation. This is equal to SW0, and this is also equal to SW0. So probably more than I needed to say about this, but the point is that we can then take this parameter, subtract this parameter off the left-hand side, divide both sides through by this term here, and we end up with this relationship here, right? So take this term out here, divide both sides through by this term here, and you get this. And so that means that this effective saturation, which really is the ordinate of this location. So this starts at an effective saturation here is equal to 0, and this is equal to 1. So we can lop off this inaccessible region of the graph just by doing this little transformation. And all that's important is that now our new parameter that we'll use is this effective saturation, which just varies from 0 to 1 from this point onwards through to here. That's all. We just rescaled it. And if we do that, then it actually plots in exactly this form. And that allows us to be able to say the things about this curve. It might not seem immediately obvious why we want to do that, but we can define this behavior in terms of this point here. So in terms of log saturations, the effective saturation here is equal to 10 to the 0. So this is equal to 1. At 1, we still don't have the bubble of air penetrating it, so this by definition has to be the bubbling pressure. And as we increase the capillary pressure by going in this direction, then we slowly move down this curve. And so if we go to this particular pressure here, we'd found ourselves at a location on this curve. And so that's what this equation is merely saying. We can identify this as being this relationship. We take log of each side and transform this. This exponent becomes a multiplier on the log, and therefore this equation, conveniently, if we think of log as a term, this is just equal to y is equal to lambda times x. Right? It's just the equation of a straight line. And so in log-log space, because of this, we've retransformed it into being a straight line. And so what we could do, in addition to this, is we could also divide this term here through by the bubbling pressure divided by the unit weight. And if we did that, we'd end up with this term here, right? Because both the unit weights, top and bottom, would cancel out, or the log of those. And so that's all we're doing. It's attempting to do. And so that's useful to us because this now says something, it's a convenient way to be able to represent the relationships. It's not kind of a random curve, which we don't really understand very well, but it's a straight line. And so it's quite easy to be able to look at the features of that straight line. And I suppose there are two ordinates that we'd be interested in. One would be the location at which a bubble of air first goes into the system. And the second one is the gradient of this line as we go up and down here. And we talked about this already briefly, but it's not bad to do it again. This is in terms of not the ratio of the bubbling pressure, but the absolute value. So this is a pressure divided by a unit weight, so it's in units of length by definition. And the ordinates that we're interested in would be, this would be the bubbling pressure here. It's increasing to the right. A larger negative value would be a larger negative pressure in the water. The capillary pressure is positive because it's the subtraction of the non-wetting minus the wetting, but the water pressure is negative because it's in tension. So a larger bubbling pressure would, on this, relate to this. Right? We talked about this before. So number 4 would be here. It's the largest of these bubbling pressures. And so as you go to the right here, you go progressively up in this scale here. And physically what that would mean would be progressively a smaller and smaller pore throat diameter as you go up in this direction. It would say something about it. The other feature of this is what we referred to as this lambda. So if we go over 1 log cycle, so a pressure difference between 100 centimeters of water and 1,000 centimeters of water, so a meter to 10 meters, these are very big numbers, you realize, gives you 1 log cycle. And if you measure the height of this in terms of 1 log cycle, this gives you the value of this exponent. That's the definition of this term. And so physically what that means, I suppose you could imagine this being two different gradients. So if you had a log cycle, this is the log cycle here that defined this. So I guess this would be, for one log cycle, this would be a lambda value which is large. So a very steep lambda is a very steep curve is a large lambda. Physically what that means is as soon as you invade it into this biggest pore throat that you get, biggest pore throat that you get into it, all of a sudden it wants to invade the rest of your porous medium. And so you'd think that a very steep value of this curve, such as number 2 here, which we talked about before, would represent a very flat response in terms of this capillary pressure curve here. As soon as you invade it for one pore size, well, there's lots of other pores that are only slightly smaller than that. So a smaller pore pressure increase allows you to invade all of those as well. And so the features of this are higher bubbling pressure would move the bubbling pressure up here. A steeper curve would represent a flatter portion of this bubbling curve. A shallower curve, such as number 4, is given by this gradient. So those are the features. So that's what defines Brooks scoring. So they're developed, they're empirical. All we're doing is plotting these exact same data here in terms of log effective saturation and log capillary pressure. The only other thing that we're doing is that in working out the saturation is we're truncating these curves at this point here as well. So that this magnitude here is equal to 0, and this curve is equal to 1, and we're able to transform them based on that. Yeah, and you get the, I guess that's an explanation of exactly what we talked about. So I suppose the one useful thing about this is that we also know that in terms of these entry pressures, we know that this should be equal to a value of J of equal to about 0.3 or 0.4. We know why. And that the value of this bubbling pressure is given by this expression here. And out of these terms, we might know a permeability, we might know a porosity, we might know the interfacial properties of the fluids that are invading on the quartz. And if this is equal to 0.3 or 4, 0.3, then the final remaining term gives us some information. So that would say how high our column of fluid would rise, and it would also say how large a pressure we have to exceed it by to be able to push it into the formation. So it says something about what this saturation profile would look like, which we talked about last time, is because it scales with capillary pressures and relative to the bubbling pressure, we can figure out exactly what these profiles of saturation might be in the vadose zone or in a complementary way below the water table for denser than water liquids. So the other way that we can approach this is to take advantage of empirical correlations. And they use the same ideas as the Brooks-Corey relationships, developed by a Dutch guy, called Van Genuchten, working in the US at the time. And it uses the same transform as we talked about before. So volumetric moisture content defined as equivalent to the residual volumetric content. So this is what we've called phi W0. This is the irreducible moisture content in the system. This is the saturated water content, moisture content, and this is the residual. So we could divide this through by the saturated moisture contents, and each one of these, theta S and theta S. And if we do that, then this just becomes, this term becomes 1, and we can subtract this term off to the left-hand side, divide both sides through by this term here, just as we did before, right? Remember, we rationalized that we would take this term, divide through by the volumetric, saturated volumetric moisture content, and then subtract this term off to the left-hand side and divide both sides through by this term here to get this relationship here. All we're doing is exactly the same in this. Not important to really understand that here. And so we get a relationship that defines the effective volumetric moisture content or the effective saturation as a function of matrix potential. This is capillary pressure divided by unit weight of water. I guess the reason that we can get away with this being just a fluid pressure the reason that this is written just as a fluid pressure is that the capillary pressure for the vadose zone, I guess it follows exactly from that curve that I drew, is that this is the pressure in the water, this is the pressure in the air. Since the density of air is 1,000th of the density of water, this is essentially 0. The air pressure is 0. So if you go up 10 feet in air, the pressure change is 0. And the pressure is 0 if you're using atmospheric pressure, if you're using gauge pressure, in which case atmospheric pressure is 0. And so we can take this as being 0. And so this really is the actual pressure in the water in the term. And the point is that this now defines the capillary pressure versus saturation curve, either as a volumetric moisture content or as a saturation. They're complementary to each other. These equations are exactly the same as each other because these effective saturation and effective volumetric moisture content are identical to each other. But now it's defined in terms by some empirical parameters. And Fetter, even though you don't have Fetter uses these m, n, and alpha values. And it notes again that these capillary pressure versus saturation curves are defined in terms of these curved curves relative to the bubbling pressure, a saturation of 1, and an irreducible moisture content. And so this is just an equation that defines these particular curves. And if we want to be able to define this capillary pressure versus saturation curves, we just need to figure out exactly what these m, n, and alphas are. And so that may seem like kind of a circular exercise, because if we know what the curve looks like, we have the curve. So why should we care about defining these relationships? Well, one reason for doing that is that if someone before you, for a particular gradation of soil, has determined what these values of mn and alpha are, then perhaps you, if you have that exact same gradation, you can co-opt those magnitudes and you can reconstruct the curve for those. So that's the rationale here. The other reason for doing this is that these constants not only allow us to redefine these capillary pressure versus saturation curves, but they also allow us to reconstruct capillary pressure, relative permeability versus saturation curves. The other thing that we want to know in terms of looking at the behavior of these soils. And I suppose just from seeing the thing at the bottom of this page, it's important perhaps to note that in Fetter's book, the use of these n is not porosity. N is equal to a coefficient which is a function of this other parameter m. So just for now, forget the fact that we've used n for porosity, but we're not using it here. The other thing that's of use is that this value of alpha is roughly equal to 1 over what we've called h sub c. Remember when we talked about the height rise within a capillary, we talked about this being h sub c 0. I guess if we drew the capillary pressure versus saturation curve next to this, it would look exactly like this as well. I meant to change the color, but I didn't, apparently. Then this, this here is HC0, which is equal to PC0 over the unit weight of water. That's how these relate to each other, which you know. And so the utility of this term alpha is that it's equal to the reciprocal of the bubbling height. And so if you think of 1 over alpha is equal to the height rise. Right. Alpha equals HB, flip it upside down, 1 over alpha is equal to HB. So this term here is what we've called HC0. That's quite a useful term in a physical sense. And so the goal here then is to figure out exactly how we might determine what these three parameters are that we need. We need a value of m, a value of n, and a value of alpha. And somehow together, through these expressions, we want to be able to figure them out from this particular curve. And so there's a recipe to this. I'm not sure it's important to understand it, but it's pretty straightforward to do. It is a recipe. And so if we look at the individual curves that we have, then this is just an example of one that has volumetric moisture content on the bottom. So the saturated volumetric moisture content is equal to 0.5. So this would be a porosity of 0.5. The irreducible saturation of water, or water content, is equal to 0.1. So I guess this would be a saturation of 20%. Right? By definition. So this is 0.1, this is 0.5, 20% is this length proportional to this. And so the recipe is just to take the average of the moisture contents between these. So we have a saturated moisture content and an irreducible moisture content, which are 0.1 and 0.5. Add them together and divide them by 2 as the average. And so for us, it's 0.3. So 0.3 represents this portion here. To draw a curve which is tangent to this line that goes through that mean point here, which is this line here, and define its slope over 1 log cycle. So this is 10 to the 4, this is 10 to the 2, this is 10 to the 3 in terms of pressure divided by unit weight of water. So this is the same as head. And so 1 log cycle is this, which is this, which is this length here. So for 1 to the length of this is equal to 0.34. Right? So this goes between here and here. So 0.1, 0.2, 0.3. Is it 4? I guess it's right down here, right? So this is 0.34. I realize I'm doing a lot of scribbling on this. To take the ratio of this average content and the slope, which is these two variables here. So it's 0.34 divided by 0.4, which is 0.85. And then to get m from the value of this coefficient, depending on whether it's between 0 and 1 or greater than 1. Obviously this is between 0 and 1. So if we plug this value into here of 0.85 and take the exponential of it, we get a value of m which is equal to 0.5. And if we use this in the two final equations, we get the other coefficient, which is just 1 over 1 minus m. This is equal to 0.5. And 1 over 1 minus 0.5 is 1 over 0.5, which is 2. And the value of alpha is given by this term. So again, we have this value, we have this value. I won't go through the math, but we end up with a value of alpha being equal to unit weight divided by the pressure times 1.73. And so if we wanted to, I guess we could rearrange that in terms of alpha to get this. And so immediately from this, if we wanted to, the value, this term here, is equal to 1 over h. And so we can immediately get the height rise in our system. So I suppose the only moral of this is that we end up getting these values of these empirical constants, m, n, and alpha for our system. And with those, if we wanted to, we could go back and substitute them into either this expression here or this expression here and come up with these curves. So it seems almost like a circular argument because we've had these curves, we've determined what mn and alpha are from the curves, and now we can reconstruct the curves. Not very useful to us. But it is useful to us because these terms can also be used to figure out exactly what the hydraulic conductivity is in terms of relative permeabilities. And so we know that in trying to calculate, we know that the flow rate is equal to cross-sectional area multiplied by the Darcy velocity, which is equal to area times relative permeability times permeability divided by viscosity times the pressure gradient. We typically would measure this in situ, same for any material, irrespective of the fluid that's flowing. And if we know what the pressure gradient is and the cross-sectional area of flow, as long as we know the relative permeability, we have a value of the flow rate through our system. And we said last time that we can use this to calculate the mass that's removed as a function of the volumetric flow rate times the concentration of the stuff that's dissolved in water. And so it's important for us to be able to get the magnitude of this relative permeability. And so one way that we can do that is also to use these same coefficients where we define a relative permeability. So in other words, in this case, this is a conductivity. This is the same as relative permeability. So this is the saturated hydraulic conductivity, right? So the saturated hydraulic conductivity is just the hydraulic conductivity. If it's 100% saturated with water, it would be a different hydraulic conductivity. I guess if it wasn't water, it wouldn't be hydraulic conductivity. But if it's what we define as a hydraulic conductivity, which is in terms of meters per second, if we were flowing air in it at a given viscosity, a given temperature, so its viscosity and density are defined, then it would have also a given saturation. Well, I'm going to leave that argument. This is just the relative permeability. So the take-home message is that the relative permeability can merely be defined as a function of how the saturation changes and as a function of these empirical coefficients, m, only m in this particular case. Or it can be defined as a function of, so this is defined as a function of saturation. Of course, as you see, because it's got this term in it. And this is as a function of pressure. And it's a function of pressure since pressure is equal to head multiplied through by unit weight of water, right? And so if I draw this curve here, if I draw these two curves on top of each other, again, you've seen these curves too many times, but no, not that one, sorry. Between 1 and 0. So I guess the only point I want to make is that if you're existing on this curve somewhere, then you can define your saturation, and that saturation would de facto give you a value of relative permeability. Right? So if this is the point of the pressure curve you're on, and you know your saturation, then you certainly can determine relative permeability. But if you only know, if you're also at a particular capillary pressure, then that also defines your same location and the same relative permeability. And so you can define yourself in terms of saturation by knowing this point through here, or capillary pressure by knowing this point here. That's all I'm doing. And so either way, you're defining a relative permeability. It would be the same relative permeability because you're coming to this point here. It's just defined in terms of what is more convenient to you, for you to know. If you know the saturation, then you use this. And if you know the pressure, you can use this. And so again, these are determined in terms of these coefficients m, n, not the porosity, and the value of alpha. And if we have those from our previous curves, which we talked about up here, the method of deriving those individual terms, then we have everything we need to know to be able to say something about the relative permeability curve, which we'd want to know if we wanted to know how fast water was flowing in our system, and hence how quickly we'd be removing dissolved components from our system. Okay? So that's it. And so I guess the final word on this is that if we knew these values of these empirical coefficients, not from having a capillary pressure versus saturation curve, but from someone else before us having done that and relating it to something else like the gradation, then we could use that data, those data, plural, to say something about what those empirical coefficients are. And so it turns out that those data exist, and it's really represented on this sheet here. The only thing that this sheet here is that Fetter and the terminology that we've used has been this. And I guess 408. What we've used in the previous derivations are m and n as these coefficients. This particular handout uses, nice and confusingly, gamma and beta. So they're slightly different. Both use the value of alpha that we did before. And so in this particular table, then I guess beta is equal to what we've called before our value of n, not porosity. And this is our value of alpha in units of 1/length, centimeters to the -1. These are the moisture contents that we're using. I guess this is what we've called phi sub s. This is residual moisture content. This is phi dot r. And it gives these values for the relative permeability. It's actually the same as the curves we mentioned up here, but they're just given here. So this gamma, if you like, is equal to our m. This beta is equal to our n. And this alpha is equal to our alpha. And the reason for switching those terminologies is it just that this table of empirical coefficients uses those empirical coefficients. And so if you know from your gradation, in your sieving of your soil that you've taken back to the lab, that's either clay or a silt or a sand by its gradation, then you immediately have the appropriate coefficients here. If you have these coefficients, you can substitute them into this expression here, and you get a relative permeability. This is just relative permeability as a function of the effective saturation. A function of, not multiplied by. So you have immediately from this a curve that looks like and from this bottom equation you have the corollary to it, which again you've seen many times. And I guess these match up, right? And this term here is this curve. And so, I guess to bring things full circle, we can reconstruct these curves from these empirical relationships where these coefficients exist for a variety of different gradations of materials. That's it. And so instead of using very simple Capri models, which are binary, to be able to reconstruct the behaviors of these systems for Capri tubes, we can get the real deal, which represents, at least for the wetting phase, the relative permeability and the Capri pressure in what we'd call drainage, I guess. And we can reconstruct these curves for these media. And then, I guess finally, we also need to remind ourselves that if we can define these curves through these empirical relationships, then that's useful to us because there's nothing special about saturated and unsaturated materials, but these curves are the same above the water table as they are below the water table. And so this curve is the same for any non-wetting fluid. And if it's air, that's great. That's what we've just defined for these Van Genuchten relationships, capillary pressure and relative permeability curves for air and water systems, the water phase in this particular case. But it also applies if the non-wetting phase, instead of being air, is actually equal to the DNAPL. And everything that we've done with those applies in that particular circumstance. And we should be able to make the transition. And I think that's it.